Welcome friends for the lectures on dynamometer. Dynamometer is a brake, but in addition it has a device to measure the frictional resistance. Knowing the frictional resistance, we may obtain the torque transmitted and hence the power of the engine. In short, the dynamometer, it is a device by which we can measure the power of the engine. There are two types of dynamometer. One is the absorption type dynamometer and another one is the transmission type dynamometer. Absorption type dynamometer means the entire energy or the power produced by the engine is absorbed by the friction resistance and the frictional resistance of the brake and is transferred into the heat during the process of the measurement. Whereas the transmission dynamometer, the energy is not wasted in the friction, but it is used for doing the work. The energy or power produced by the engine is transmitted to the dynamometer to some other machines where the power developed is suitably measured. First we will see the absorption type dynamometer. In the absorption dynamometer there are two types, the Prony-Brake dynamometer and the row-brake dynamometer. The first, the Prony-Brake dynamometer, which is the simplest dynamometer. It consists of two wooden blocks placed around the pulley fixed to the shaft of an engine whose power is required to be measured. The blocks are clamped by means of the two bolts and the nuts as shown in figure. You can see in this figure. A helical spring is provided between the nut and the upper block to adjust the pressure on the pulley to control its speed. The upper block has a long lever attached to it and carries a weight W at its outer end. A counterweight is placed at the other end. You can see on the left hand side there is a counterweight of the lever which balances the brake when it is unloaded. Two stops S and S are provided to limit the motion of the lever. When the brake is to be put in operation, the long end of the lever, it is loaded with suitable weight W and the nuts are tightened until the engine shaft runs at a constant speed and the lever is in horizontal position. Under this condition, the moment due to the weight W must balance the moment of the frictional resistance. So let us take weight W at the outer end of the lever. L, it is the horizontal distance of the W, and F, it is the frictional resistance between the block and the pulley. R, it is the radius of the pulley, and N, it is the speed of the shaft. So we know that the moment due to this weight W into L, that is equal to the moment of the frictional resistance, that is F into R. And that F into R, it is nothing but the torque. So the resistance or the torque of the shaft, T, it is equal to W into L, it is equal to F into R. So work done in one revolution, that is torque into the angle turn in radians. So T into 2 pi n Newton meters. So work done per minute, if you multiply by speed, that gives you the work done per minute. So T into 2 pi n Newton meter. So we know the brake power, it is the work done per meter divided by 60. That means if you convert that into work done per second, so T into 2 pi n divided by 60 and T means W into L. So the second absorption type dynamometer, that is the row brake dynamometer. In the row brake dynamometer, 1, 2 or more ropes wound around the flywheel or a ream of the pulley fixed rigidly to the shaft of an engine. The upper end of the rope is attached to a spring balance, while you can see in this diagram, the upper end is attached to the spring balance while the lower end, it is attached to the dead weight. In order to prevent the slipping of the rope over the flywheel, wooden blocks are placed at the interval around the circumference of the flywheel. You can see here that there are 4 wooden blocks, it is kept around the flywheel. In order to prevent the slipping of the rope over the flywheel, wooden blocks are there. In the operation of the brake, the engine is made to run at constant speed. The frictional torque due to the rope must be equal to the torque being transmitted by the engine. So let us take W dead weight S it is the spring balance, D it is the diameter of the wheel, small d diameter of the rope, and N it is the speed of the engine. So net load, it is the dead weight minus the spring load, right? So W minus S in Newton. We know that the distance moved in one revolution, that is pi into d. Now here it is d, it is the diameter, capital D it is the diameter of the drum plus the diameter of the rope, if you want to consider. So work done per revolution, it is W minus 8 into pi in bracket d plus d. So work done per minute, it is W minus S pi d plus d into N, and therefore the brake power, it is work done per minute divided by 60. So W minus S into pi in bracket d plus d into N divided by 60, and if you neglect the rope diameter, then it will become W minus S pi into d into N divided by 60. Then the transmission dynamometer. In transmission dynamometer, there are three types: epicyclic train dynamometer, belt transmission dynamometer, and the torsion dynamometer. In epicyclic train dynamometer, there is a spur gear, annular gear, and the pinion. The spur gear is key to the engine shaft, that means driving shaft, and rotates in the anti-clockwise direction. You can see in this diagram. The annular gear is also key to the driving shaft and rotates in the clockwise direction. The pinion on the intermediate gear meshes with both the spur and the annular gear. The pinion revolves freely on a lever which is pivoted to the common axis of the driving and the driven shaft. A weight W, small w, you can see on the left hand side, it is placed at a smaller end of the lever in order to keep in a position. A little consideration will show that if the friction of the pin on which the pinion rotates is neglected, then the tangential effort P exerted by the spur gear on the pinion and the tangential reaction on the annular gear on the pinion are equal, and therefore you can see in this diagram both are acting upward. Since these efforts act in the upward direction, and therefore the total upward force on the lever acting through the axis of the pinion, it is P plus P, that means 2P. This force tends to rotate the lever about its fulcrum, and it is balanced by the dead weight W at the end of the lever, and therefore you can say 2P into small a, and that is equal to W into L. So for equilibrium, you can write here, for equilibrium of the lever taking the moment about the fulcrum F, 2P into A, it is equal to W into L, or P it is equal to W into L divided by 2A. Now let us take R, capital R, it is the P circle radius of the spur gear, and N it is the speed of the engine. So torque transmitted, it is P into R. So the power transmitted, it is T into omega, right? 2 pi n by 60. So and T it is equal to P into R. And how to calculate P? P, you can calculate WL divided by 2A. So this is the which type of dynamometer? It is the epicyclic train dynamometer. Then the next one, it is the belt transmission dynamometer, and in that the Ford or Thornycroft transmission dynamometer. When the belt is transmitting power from one pulley to another pulley, the tangential effort on the driven pulley is equal to the difference between the tension in the tight side and tension in the slack side of the belt. A belt dynamometer is introduced to measure directly the difference between the tension of the belt while it is in running. It consists of a pulley A, you can see in this diameter, this bigger pulley, it is A, called a driving pulley, which is rigidly fixed to the shaft of an engine, right, whose power is required to be measured. There is another pulley B called a driven pulley mounted on another shaft to which the power from pulley A is transmitted. The pulleys A and B are connected by means of the continuous belt passing round two loose pulleys, that is C and D, which are mounted on a T-shaped frame. You can see here, this C and D, it is mounted on a T-shaped frame. The frame is pivoted at point E and its moment is controlled by the two stops S and S. Since the tension in the tight side of the belt is T1 is greater than the tension in the slack side of the belt T2. The total force acting on the pulley C, in this diagram you can see this force, total force tension is T1, this is also T1, so total tension it is acting on the pulley C, it is 2 times T1, and the tension acting on the pulley D, it is 2 times T2, right? So T1 is greater than T2, so definitely 2T1, that moment it is in the anti-clockwise direction above T, and the moment of 2T2 it is in the clockwise direction, as well as the moment of W into L, that is also in the clockwise direction. So in order to balance this, now taking a moment about the pivot E, neglecting the friction, 2 times T1A equal to 2 times T2A plus W into L, and from this equation you can write T1 minus T2, it is equal to WL divided by 2A. Now let us take D, it is the diameter of the pulley A, N it is the speed of the engine shaft. So work done in one revolution, T1 minus T2 into pi into D, Newton meter. And the work done per minute, it is T1 minus T2 into pi D N, Newton meter. So the brake power, it is work done per minute divided by 60. So T1 minus T2 pi dn divided by 60, that you will get in watts. And the third type of dynamometer in transmission dynamometer, that is the torsion dynamometer. This is used for measuring a large power, particularly the power transmitted along the propeller shaft of the turbine or a motor vessel. A little consideration will show that when the power is being transmitted, then the driving end of the shaft twists through a small angle relative to the driven end of the shaft. The amount of the twist depends upon many factors such as torque acting on the shaft, T, length of the shaft, diameter of the shaft, and modulus of rigidity of the material of the shaft. We know that the torsion equation is T by J, it is equal to G theta by L, which you have seen in the MOS, or T it is equal to Gj divided by L into theta. Here T it is the torque, G it is the modulus of rigidity, J it is the polar moment of inertia, and L it is the length of the shaft, and theta it is angular twist. Now Gj by L, this term is constant because G it is property of material, J it is depend on diameter, if diameter is fixed your J is fixed, L it is the length of the shaft, that is also fixed. So T it is directly proportional to theta, and therefore you can say if the angle of the twist is measured by some means, then definitely the torque and hence the power transmitted may be determined. Then the type of this torsion diameter, that is the Bevis-Gibson flashlight torsion dynamometer. Now here it is depend on the fact that the light travels in a straight line through a air of uniform density and the velocity of light is infinite. We know this. In this Bevis-Gibson flashlight torsion dynamometer, there is two discs A and B fixed on a shaft at a convenient distance apart. Each disc has a small radial slot, and these two slots are in the same line. When no power is transmitted and there is no torque on the shaft, a bright electric lamp L behind the disc A is fixed on the bearing of the shaft. This lamp is masked, having a slot directly opposite to the slot disc A. At every revolution of the shaft, a flash of light is projected through the slot in the disc A towards the disc B in the direction parallel to the shaft. And eyepiece E, you can see in this diagram, second diagram, that eyepiece E, it is fitted behind the disc B on the shaft bearing, and it is capable of slight consequential adjustment. When the shaft does not transmit any torque, a flash of light may be seen after every revolution of the shaft, right? As the position of the slit do not change relative to one another. Now, when the torque is transmitted, now see the third diagram, when the torque is transmitted, the shaft twist and the slot in the disc B changes its position. So A and E are still in line. Due to this, the light does not reach to the eyepiece. If the eyepiece is now moved around by an amount equal to the lag of the disc B, then the slot in the eyepiece will opposite to the slot in the disc B, and hence eyepiece received a flash of light. The eyepiece is moved by operating a micrometer spindle, and by means of scale and vernier, the angle of twist may be measured up to 1/100th of the degree. Right. So this is about. Now if this torsion meter discussed above gives the angle of the twist of the shaft when the uniform torque is transmitted during each revolution, as in case of turbine shaft. But when the torque varies during each revolution, as in the reciprocating engine, it is necessary to measure the angle of twist at a several different angular position. For this, the disc A and B are perforated with the slot arranged in the form of the spiral. You can see in this diagram, these are the slits which are provided here, but these are arranged in the spiral form, right? So if there is a variation in the torque during the revolution, then you have to use the slitted or perforated disc like this. So this is about the dynamometer. Friends, take care and